Hello my dear
Hello.
students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. So we have learned previously that the total energy in any section in the pipe can be written as P by rho g plus Z plus V square by 2g, where P by rho g indicates the pressure head, Z is the position head, and V square by 2g indicate the velocity head. And we have also learned that the pressure energy is decreased in the direction of the flow. If you are writing the expression for total energy for an open channel flow, it is equal to y plus z plus v square by 2g. So figure shows the section of an open channel. So z is the position head and y that indicates the flow depth, and v square by 2g is the velocity head. So if you are comparing the total energy equation for this pipe flow and in open channel, we can see that the pressure head in pipe flow is analogous to the flow depth in an open channel. Now, if channel bottom is taken as datum, total energy per unit weight, that is equal to E equal to y plus v square by 2g, or it can be written as y plus q square by 2ga square, where v equal to q by a. So we can say that specific energy is the energy per unit weight of water measured above the channel bottom. So the concept of specific energy is very useful in the solution of many open channel flow problems. Now let us discuss about the specific energy curve. So the expression for specific energy E equal to v square by 2g plus y, or it is equal to q square by 2ga square plus y. So the first term represents specific kinetic energy and the second term represents the specific potential energy. So specific energy E can be written as Ek plus Ep. Ek is the specific kinetic energy and Ep represents the specific potential energy. So for a given channel section and discharge, specific energy E equal to function of y, or Ek is a function of y, or Ek equal to q square by 2ga square is a function of y, and Ep equal to y. If you are plotting variation of E with respect to y, which is the summation of Ek plus Ep. So initially we can plot Ek with respect to y. So this parabolic curve represents the variation of Ek with respect to y. In the next step, we can plot the variation of specific potential energy with respect to y. So that means Ep equal to y, which represents a straight line by making an angle 45 degree with respect to horizontal. So this straight line which represents Ep equal to y. But specific energy E equal to Ek plus Ep. If you are adding the value of Ek and Ep for corresponding value of y, then the resulting curve is represented in blue color. So this curve represented as E equal to Ep plus Ek, which is equal to y plus v square by 2g. It is indicated by the notation ACB. So this curve ACB represents the variation of E with respect to y, and it is called specific energy curve. So this curve ACB has two limbs, CA and CB. The limb CA, which is going asymptotically towards this energy axis, whereas the limb CB, which is going asymptotically towards this potential axis. And when you are observing this curve ACB, you can see that when the y value increases from low to high, the specific energy decreases and it reaches a minimum value. Then it started increasing with increasing value of y. So the point C, which represents the minimum value of specific energy, and the flow condition corresponding to this minimum specific energy, that is called critical flow condition. Let us consider a point on this energy axis, and if you are drawing a vertical, then it will cut this specific energy curve at these 2 points. So these are the 2 points. That means for each specific energy other than this minimum specific energy, there are 2 depths are possible, y1 and y2. So the depth y1 is below this critical depth yc, and the depth y2 which is higher than this critical depth yc. So these 2 depths y1 and y2 are called alternate depth. So we can say that for each specific energy other than this minimum specific energy, there are 2 depths are possible, and they are called alternate depth. The point C where specific energy is minimum. So how will you find out the minimum value of specific energy? So for a given channel section and discharge, E is the function of Y. The condition of minimum specific energy can be determined by differentiating this E with respect to Y and equating to 0. So E equal to Q square by 2G A square plus Y. So if you are differentiating this expression with respect to Y and equating it to 0, then it becomes 1 minus Q square by GA cube into dA by dy equal to 0. So in this, Q is constant and A is a function of Y. For the channel section, as shown in this figure, the top width T represents the width of the channel at the free surface. So consider a small strip of water with thickness dy. So area dA, which is equal to T into dy, or T equal to dA by dy. So if you are replacing this dA by dy in terms of T, then this equation becomes 1 minus Q square T by GA cube equal to 0, or Q square T by GA cube equal to 1. So this condition represents the minimum specific energy. So this equation represents the condition of minimum specific energy irrespective of the shape of the channel. Now let us discuss about the various equations which can be utilized to represent the critical state of flow. So during critical state of flow, flow depth is critical. Similarly, flow velocity is known as critical flow velocity. So Q square T by GA cube equal to 1. So this is the condition to represent the critical state of flow irrespective of the shape of the channel. So if you are modifying this equation, we can represent this equation as Q square by G equal to AQ by T. But A into root of A by T, that is equal to Z, that is the section factor. So this equation now can be written as Q by root of G equal to A into root of A by T, that is equal to the section factor at the critical state. So we can say that in critical state, section factor ZC equal to Q by root G. So when the flow is critical, if you know the discharge, then we can calculate ZC and correspondingly we can calculate the critical flow depth. So that is the advantage. Similarly, this expression we can represent it as Q square by A square G equal to A by T. So Q square by A square is replaced by V square. So this equation turned into V square by G equal to D. D is hydraulic mean depth represented by A by T. So if you are dividing LHS and RHS by 2, then this equation becomes V square by 2G equal to D by 2. So remember, in critical state of flow, velocity head equal to half the hydraulic mean depth. So from this expression, we can write V by root of GD equal to 1. So this is another criteria to represent the critical state of flow. So I will repeat, in critical state of flow, Q square T by GA cube equal to 1, or section factor equal to Q by root G, velocity head equal to half the hydraulic mean depth, and Froude number equal to 1. So all these equations are valid and can be used to represent the critical state of flow irrespective of the shape of the channel. So to conclude, we can just list out the characteristics of critical flow. During critical flow, specific energy is minimum for a given discharge. Discharge is maximum for a given specific energy. Froude number is unity. For a small sloped channel, velocity head equal to half this hydraulic mean depth. So all these equations are valid to represent the critical state of flow irrespective of the shape of the channel. Now let us consider a rectangular channel. So in a rectangular channel, the top width T and bottom width P is same, and the equation representing the critical state of flow is Q square T by GA cube equal to 1 and Q by root of G equal to A into root of A by T. For a rectangular channel, we can represent the discharge Q equal to small q into B in such a way that this small case q represents the discharge per unit width. So if you are representing capital Q equal to Q into B and substituting in this expression, you will get QB by root G equal to A is represented by B into YC into root of BYC by B. So if you are simplifying this expression, you will get Q square by G equal to YC cube, or critical flow depth equal to cube root of Q square by G. So remember, this expression is valid for a rectangular channel. So Q represents the discharge per unit width. So the specific energy equation that is v square by 2g plus y, that is equal to q square by 2g a square plus y. So this equation also we can represent in terms of discharge per unit width as qb square by 2g into by square plus y, or we can simplify this expression as q square by 2gy square plus y. So for a rectangular channel, we can express specific energy as E equal to q square by 2gy square plus y. And this equation can be modified as q equal to root of E minus y into 2gy square. For a constant specific energy E, the discharge per unit width Q is plotted against the depth of flow. So this curve represents the variation of discharge per unit width with respect to y is called discharge curve. So you can see that Q attains a maximum value at a particular value of y. So how will you find out this maximum value of Q? So the condition for this maximum discharge Q max may be obtained by differentiating this expression Q with respect to y and equating to 0. So for a given specific energy, the condition for discharge per unit width Q to be maximum by differentiating Q with respect to y and equating it to 0. So if you are differentiating this expression, so this is the differential form. So if you are putting numerator equal to 0, you will get E equal to 3 by 2 y. Since it represents the critical state of flow, we can rewrite this expression as EC equal to 3 by 2 yc. The figure shows discharge curve, and you can see that Q max is corresponding to the critical depth of flow, where yc, which is equal to 2/3 E. The concept of specific energy is very important in the solution of many open channel flow problems. So for a triangular section, the relationship between specific energy and critical flow depth is written as EC equal to 5 by 4 yc, and for a parabolic section, the relationship EC equal to 4 by 3 yc. From earlier discussion, it is found that the condition of minimum specific energy represents critical state of flow where Froude number equal to 1. So what is the definition of Froude number? Froude number equal to V by root of Gy. So at this point, Fe, that is equal to V divided by root of Gyc, because here the flow depth is critical flow depth. When the flow depth increases beyond Yc, the Froude number decreases, and this represents the subcritical state of flow or transcritical flow. And for all depth below the value of Yc, the Froude number increases and it is higher than 1. So the flow condition below this critical state of flow represents subcritical flow or shooting flow, whereas the flow condition above this critical state of flow represents subcritical flow or transcritical flow. So Froude number equal to 1 represents critical state of flow, whereas Froude number is less than 1 represents subcritical flow, and it is higher than 1 represents supercritical flow. The Froude number is the dimensionless number, can be utilized to classify the state of flow as critical state of flow, subcritical state of flow, and supercritical state of flow. Now let us discuss about the critical slopes. So critical slope is the value of the slope at which the uniform flow at a specified discharge Q occurs under critical flow conditions. Since it is the uniform critical flow, all the flow depth at different sections that is equal to critical flow depth. So we can utilize Manning's equation or Chassis equation for the computation of discharge. Now the session comes to an end. For the time being, it is enough. All the related problems are discussing at the end. Next video discusses about gradually varied flow. Please don't forget to press the bell button to get the notification of next video. Thank you.